Hello everyone, we are at the topic of diodes. We are looking at waveform shaping circuits using diodes, and in today's lecture we are going to study peak detector circuits. Here is our ideal peak detector circuit. It consists of a diode that is connected to a capacitor, and the output is taken at two terminals of the capacitor. As the name implies, this circuit detects the peak value of the input signal. When the input signal reaches its peak value, the output is going to be almost equal to the peak value of the input signal, and it's going to stay constant even when Vi goes below its peak value. So V out is almost equal to peak value. In fact, it's V peak, the peak value of Vi minus Vd naught volts. Let's analyze this circuit. First, let's take a look at the case when the diode is off. We're going to assume that the initial voltage across the capacitor is equal to 0. So labeling the voltage across the diode, Vd and Id. Considering this node as a reference node, this is Vc, this node is equal to Vi. So Vd is Vi minus Vc, which is initially equal to Vc is equal to 0, so Vd is equal to Vi. From there, when the diode is off, I know that Id is equal to 0 and Vd is less than Vd0. Because Vd and Vi are equal, that means Vi is less than Vd naught. So for Vi values less than Vd naught volts, the diode is going to be off, and we can replace it with an open circuit. So V out is equal to Vc, which is equal to 0 initially. So for this time range, as you can see, the diode is off and V out in this range is equal to 0. I'm plotting V out of t as a function of time with blue color. When Vi increases from Vd naught volts, the diode is going to turn on. I can replace the diode with its circuit model when it's on, which is a constant voltage drop model. And I'm going to write Vd is equal to Vd0. This is plus minus Vd. And Id is going to be greater than or equal to 0 for the diode being on. Now the diode is on and conducts, so Vi is going to charge the capacitor. As a result, Vi out, which is equal to Vc, is going to increase. Using the KVL, I know that Vi out equals to negative Vd plus Vi. Because Vd is a constant value, I have negative Vd naught plus Vi. Vi out is slightly less than Vi. This is the equation for V out in this area. Also in this area, Id is equal to IC, and that is equal to C dVc over dt. This is IC, and that is equal to C dVi minus Vd0 divided by V dt. That is equal to C dVi over dt. Now at this time point that I'm going to label as t sub a, at t equal to t sub a, I have Vi equal to its peak value, V peak, and Vc equals to V peak minus Vd sub 0. From there, because Vd is equal to Vi minus V sub c, capacitor voltage, I'm going to write it as Vi minus V peak minus Vd sub 0. So after t equal to Ta, for other time points, the amplitude of Vi goes below V peak value. So this one goes below V peak value. As a result, Vd is going to be less than Vd naught. As a result, the diode does not conduct anymore because Vd is less than Vd naught. From there, I know that for all of these time points, V out or Vc is going to stay at a constant value equal to V peak minus Vd sub 0. So for all of these time points, the amplitude of Vi is less than its peak value. As a result, Vi minus Vc is less than Vd naught. When Vi reaches its peak value, the diode might momentarily turn on, but for the ideal cases, we're going to assume that the diode does not turn on anymore, because immediately after this time point, the amplitude of Vi decreases from its peak value. So as you can see in this graph, after Vi reached its peak value at this time point, the output is going to be at a constant value equal to V peak minus voltage drop across the diode. So this circuit detects the peak value of the input signal, and after Vi reached its peak value, the value of output is going to stay at a constant value. If you have a time varying input signal whose peak value changes over time, this circuit can be used to detect the largest peak value of the Vi signal. So as you can see, when the first peak comes, V out is going to be equal to that peak value minus VD naught. The next peak is larger than the previous one, so the value of output voltage is going to increase to that peak, to the second peak value minus VD naught point. The third peak comes, and that's greater than the second peak, and V out is going to be equal to the value of the third peak minus VD naught. The fourth peak, here this peak is less than the third peak, but the value of V out does not change because the diode cannot turn on anymore. In an ideal peak detector circuit, there is no resistive path for the voltage across the capacitor to discharge through when the diode is off. So when the diode turns off, the voltage across the capacitor stays at a constant value equal to V peak minus VD naught. Here is the circuit for a practical peak detector. As you can see in this circuit, there is a resistor in parallel with the capacitor. So when the capacitor is charged and the diode turns off, the voltage across the capacitor is going to decrease because the capacitor is going to discharge through this resistor. So for these time points, the diode is off, but the voltage across the capacitor does not stay at a constant value. Rather, its voltage is going to exponentially decrease. And then when the amplitude of Vi reaches a value that is greater than Vc plus Vd naught, then the diode is going to turn on and the voltage across the capacitor is going to increase because diode conducts and the capacitor charges some more, and again it turns off, and then again the capacitor discharges through this resistor. Using the KVL equation in the main circuit and the voltage equation of a discharging capacitor, we can find the output at any time point. We also can find the time point at which the diode turns back on. This is the voltage across the capacitor when it is discharging, and I know that from the KVL, I know that Vd is Vi minus Vc. When the diode is off, Vd is less than Vd naught, so Vi in all of these time intervals, Vi is less than Vct plus Vd naught. Also, when the diode turns back on in this time point, I know that Vd is equal to Vd naught and Id is greater than 0. So I can find the equation of V out when the diode is on. So this is a simple equation because the diode is on. I can replace it with constant voltage drop model. KVL tells me that this KVL in the main loop tells me that V out equals to Vi minus Vd naught. So I have the equation for this section of the graph. The shape of the output signal in a peak detector circuit depends on the ratio of its time constant to the period of the input signal. So tau is the time constant of the peak detector circuit, and T is the period of the input signal. In an ideal peak detector circuit, the value of resistor in parallel with the capacitor is infinity. So tau, which is equal to R times C, and this is R, and this is the capacitor for our peak detector circuit. This is our diode model when it is off, and this is my Vi, and this is V out or Vc. So time constant is equal to RC. For an ideal case, resistor value is equal to infinity. As a result, tau over T goes to infinity. In practical cases, there is always a resistive path for the capacitor to discharge when the diode is off. But in a good peak detector circuit, the ratio of time constant to the period of the input signal is much greater than 1, and if it is much greater than 1, then the capacitor cannot discharge a lot before the next peak of the input signal arrives. So the output almost maintains its shape. So when RC is much greater than the period of the input signal, the output is going to be almost equal to the peak value of VI. But for example, for this one, the capacitor is going to discharge for values of VI less than its peak value. So it totally discharges and V out is not equal to peak value of VI anymore. In summary, we looked at both ideal and practical cases for a peak detector circuit, and you saw that in a practical peak detector circuit, if the time constant of the circuit is much greater than the period of the input signal, then the output waveform is not going to depart from its expected shape. Thank you for watching.